In this particular video, we're going to look at electric and magnetic field. This is Unit 4 Physics. If you are taking IAL Physics and you're going to do Unit 4, this video is for you. We are going to have a detailed discussion on how you're supposed to approach different questions that have been asked in previous exams. So if you're new to Proflan YouTube channel, consider subscribing so that anytime I'm going to upload more tutorials, you'll be notified. And also, you can be able to check out our Patreon page where I usually upload these documents and PDF that I'm having on this particular end. So to get started, so that we can see what really we ought to have studied in this particular topic, electric field and magnetic field. So here we are going to look at concepts to do with forces with conductors placed in magnetic field, concepts to do with electromagnetic induction. So let's check out questions that have been asked, and then you can be able to see in this particular setup, we are told that the photograph shows demonstration of AC generator, and this particular AC generator that is used is just a model that is used in school. And then we are told that the handle is used to rotate the coil between the magnetic poles. So what you need to understand that when the coil rotates within the magnetic field, the coil is going to cut the magnetic field. And once the coil cut the magnetic fields, there is going to be induced EMF in that particular coil. And every time these fields keep on changing, all the coil keeps on changing side within the magnetic field, what is going to happen there is that the current is going to change direction. So in this case, we are going to say rotating the coil in the magnetic field, this causes a magnetic flux linkage. Once there is a change in magnetic flux linkage, then an EMF is going to be induced, and in the process there's going to be a flash in the LED, because the moment there is current flowing, the LED is going to shine. So when you are going to give your answer in that particular exam, you have to be very procedural in the way that you are giving your answer. EMF is induced in the coil, so the current flows in the coil, making the LED to flash. Remember, LED is a light emitting diode. So meaning that once current is flowing in a particular direction, current is going to flow. But if current is going to reverse or flow in the opposite direction, then that LED is going to remain off. So when the coil reaches the vertical position, moving parallel to the field, there is no induced EMF, so the LED is going to go off. Induced EMF changes direction when the coil switch position, and the LED will only shine once when current is flowing in one direction, because we are talking of what? A diode. We were told something to do with a diode. All right, so moving to the next question here, we are told that add on the graph to show output if angular velocity decreases. So the original graph that was given here, and then we are told that the angular velocity decreased. So if angular velocity decreased, what is going to happen? The time period is going to increase. Yeah. At the same time, the amount of induced EMF is going to decrease by a half, because the rate at which the coil is going to cut through the magnetic field is going to decrease. That's the reason why the current is going to reduce. And you can see now I did draw a waveform which is twice the period, but I have the induced voltage, because once you reduce angular velocity, it means you are going to reduce the rate at which the magnetic flux linkage is going to change. Then you are supposed, in this question, you are supposed to explain the changes in the graph when the angular velocity of the coil is halved. Then we are going to say half angular velocity means it will take twice as long, so the period will be double. But the rate at which the magnetic flux linkage is going to change is going to halve. So the EMF is going to be halved. So that is the reason as to why I did that. The coil rotates in a uniform magnetic field at the original angular velocity. The average magnitude V is 3.2. Determine the number of magnetic flux. So something that you need to understand is that induced EMF is equals to the rate of change of magnetic flux linkage. So if you want to find the magnetic flux, it's magnetic flux density times the cross-section area of the coil. So if we want to find the magnetic flux linkage, we are going to take the magnetic flux times the number of coils. So that's why you can see I first calculated the magnetic flux, which is the BA bar, which is going to be the magnetic flux density times the cross-section area. Then you need also to remember that EMF is equal to the rate of change of magnetic flux, because that is basically according to Faraday's law. Faraday's law states that the rate of change of magnetic flux, the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux. So if you want to find the EMF, just find the rate of change of magnetic flux linkage. Then in that process, that will be the answer. So in that case here, we are going now to work in this way. So we have gotten the magnetic flux. Then to get magnetic flux linkage, you need to multiply the number of turns. So N. And remember, in this question, we are working out the number of turns. So if we are working out the rate of change, there must be the aspect of time, guys. So which means that we are going to have the magnetic flux linkage, which is this value at the numerator, divided by time. But time, guys, I know most of the students will make a mistake here. The time you are going to use is not the periodic time. You are not going to use the periodic time. The magnetic flux linkage is changing from 0 to this maximum point. That's where the change of the magnetic flux is starting from 0 to the maximum. So the time you'll use for the rate of change is a quarter of a period, because the change of magnetic flux is happening from within a quarter of a period. The flux will change from 0 to the maximum. That's why there's induced EMF up to the maximum. Then it will start decreasing to 0. So always the time you are using for the change of magnetic flux linkage, guys, is going to be a quarter a period. That's why you can see I'm having the periodic time times 0.25, a quarter, because the change of magnetic flux is happening between 0 and this middle point. So a quarter of a period. And if you work it out, you are going to get the number of turns being equals to 402, because you are going to equate this value you have here to 3.2, the average magnitude of induced EMF that was given there. A quarter, because the change of magnetic flux occurs over a quarter of the period. I believe you are not going to forget that, guys. Let's look at the next point here. We are told that in 1821, Michael Faraday made what is observed to be the first electric motor. This is in 1981, guys. Okay, so that was the first believed to be electric motor, which was having a stiff wire. There is a magnet, and that stiff wire was dipped in mercury, so it could be able to rotate that, and in the process of rotating is going to cut the magnetic field. And basically that is why we are having that. So we were told that the wire made 10 complete revolutions in 8.3 seconds. So if it's making 10 revolutions in 8.3, one revolution will be what? Yeah. So 10 is equals to 8.3. One revolution will be what? That will be 8.3 divided by 10, which is going to translate to 0.83 seconds. And that is going to represent the periodic time of this particular revolution. But we know angular velocity, because we are calculating the angular velocity of the wire. We know angular velocity is given by omega 2 pi over t. So if you substitute that, you are going to get a 7.57 radians per second. That is exactly what you are going to do at that given point. The next area is the question whereby you are working out the force on a wire within a magnetic flux. Now, if a conductor is within a magnetic field and the current flows through that conductor, it's going to experience a force. The formula you're going to calculate that is BIL sine theta. Force experienced by a conductor in a magnetic field is going to be magnetic flux density B times the amount of current that is passing there times the length of that particular conductor, sine of theta. And sine of theta is the angle between the current direction and the magnetic field. So in this case here, the angle we are talking about, theta, is this angle that we have at that point. This angle here is the angle that we are talking about. But since this is 10 degrees, then this is 90, then it means we can be able to find this angle, the angle between the current conductor, or the current within the current in the wire, and the magnetic field. That angle is going to be 90, because this is 90, this is 10. A triangle make 180 degrees, then it means this is 90 minus 10, and that is going to be 80 degrees. So we can be able to say, therefore, it will be the current times the magnetic flux density, which is given here, times the current, which is given 1.1 amperes, times sine of 80. And you also have to remember times the length, but the length is in centimeters here, guys. So that's the area. Those are the areas that you have to be very keen converting units, quantities in the SI unit, so that you can be able to determine the correct answer. So in that case, you are going to get 2 times 10 raised to power 3 newtons. And don't forget to include the units and time you are going to be answering physics question. So the next part we were asked there is to describe the direction of the force experience, whereby you are going to use Fleming's left-hand rule. So you can see current is, if you are looking from your end, current is approaching you. When you are looking from your screen, wherever you are watching from, guys, and also if you are new to Proflan, consider subscribing. So you are going to use Fleming's left-hand rule. Relate your finger, left-hand finger, point to the direction of the field. Remember, you are looking on the screen, you do it the way I'm doing. Then the current's coming this way, then this particular conductor is going to experience an upward force. Yeah, so the force will be upward, and that is exactly what we ought to have done at that particular section. And let me just demonstrate it so that you can be able to see exactly what I'm talking about from my end. So I'm having this. I just want to show you so that you can be able to see what I'm having. Yeah, so that you can be able to see what I'm having here. So I'm having the conductor well seated on my table, right? And I want to use Fleming's left-hand rule. So I'm going to place my finger this way. Yeah. The field finger is pointing this direction where the field is going. The second finger is pointing where the current is going, like that. Then the thumb will be acting upwards. So basically that is how you are going to do that. You just use Fleming's left-hand rule to do that. Okay, I believe you've understood exactly what you're supposed to do there. Let's move to the third question. The third question is talking of a mass spectrometry. Yeah, in mass spectrometry, It's used, mass spectrometry is used to determine the masses of different isotopes. Atoms of isotopes are ionized and accelerated. They pass through velocity accelerator into a region with uniform magnetic field. So in accelerators, what you need to understand, the purpose of these magnetic fields that we are having at this given point, the reason as to why those magnetic fields are there is to ensure that the charge that is moving this can be able to experience a force. It can be able to experience a force so that it can be able to change direction. That's the purpose of the magnetic field. But the purpose of the electric field is to accelerate the particle, to give it a push so that it can be able to move. So you are given that an ion was placed. Ion accelerator uses electron beam to ionize oxygen. So we have 2 plates, and then there is a gap here. We are told to calculate the potential difference between the anode and the cathode. Yeah, so what we need to understand here, we are told that the electric field is 7.5 times 10 to the power 5 volt per meter. That is the electric field. Then we are supposed to work out the PD, the potential difference, guys. So what you need to remember here is that the potential difference is used to calculate electric field in 2 charged plates, which is electric field is equal to potential difference over the distance of our separation. So the distance of our separation in our case is the 6.0 centimeters. So if we want to work out this, we are going to say potential difference is going to be electric field times the distance. But you have to remember to convert these centimeters that you are having here, guys, so that you can be able to get your correct answer. Yeah. Yeah, so for you to be able to get the correct answer, you ought to do the correct conversion so that you can be able to get your answer as 4.5 times 10 raised to the power 4 volts. A stationary oxygen ion is formed halfway between the anode and the cathode. Show that the velocity of the ion as it passes through the hole of the cathode is about 5 times 10 to the power 5 meters per second. The mass of oxygen is that. So how are we going to go about this particular question? The question says it was stationary, but which force is going to be acting on this stationary oxygen ion is the electric force. And remember, electric force is given by the charge times the electric field. If a charged particle is placed within a magnetic field, that charged particle is going to experience a force, which can be calculated by the formula force is equals to QE, charge times the electric field. But from Newton's second law, we know that resultant force is equals to mass times acceleration. So meaning, if we use these 2 formulas, we can be able to find acceleration. And this is going to be charge times electric field over the mass of that charged ion. If you substitute that, you are going to get the acceleration as 4.4 times 10 raised to the power 12. Once you have gotten the acceleration, guys, you are going now to use the equations of motion, because this is going to be accelerating at a constant rate. So meaning that it's going to experience a force and it's going to accelerate, then we can be able to use v squared is equal to u squared plus 2as. But you have to remember that initially it was at rest, so v will be 0. Then we end up having v squared is equals to 2. We end up having v squared is equals to 2as. Then if you make v the subject, we can have 2 times acceleration times the displacement. But the displacement we're going to use, guys, will be a half, which is going to be a half of 6, which is going to be 3, because it was midway, yeah, between the anode, yeah, between the anode, right? Okay, so if you work it out, you are going to get 5 times 10 to the power 5 meters per second. That should be okay. Then we are told that oxygen ion enters a velocity selector. Yeah. With a range of velocities, the velocity selector allows ions with specific velocity to travel. Yeah. Then explain the direction of the magnetic field. So we are told a uniform electric field between the plates acts on the oxygen ion. A uniform magnetic field. So uniform magnetic field acts so that the magnetic force on the oxygen is opposite direction to the electric field. Okay, if we are talking of a charged, positive charged hydrogen, oxygen ion, so which means that within these plates we are going to have electric fields, and these electric fields will be acting in which direction? The electric fields will be acting downwards like that. So those are the electric fields within that particular region. So also we are having magnetic field. Yeah. So a magnetic field was introduced. We don't know the direction of this magnetic field, but what we know is that it will be the force, magnetic force will be acting the opposite direction to the electric field. So meaning this charged particle will experience a downward force. Electric force will be acting downward, but the magnetic force will be acting upward. This is the electric force. But magnetic force will be acting upward. Now, if that is the case, then we need to determine the direction of the electric field. How are we going to go about it? How are we going to go about this, guys? Yeah, we have said that the electric fields are acting downwards. Those are the electric fields. Then the force of the electric field Fe is acting downward, which will mean that the magnetic force, we are told that the magnetic force acts in opposite direction. That's what they have said here. The magnetic force acting in opposite direction. So opposite direction of the electric field will be upward. So that is the direction of the magnetic field. When an object is placed in a magnetic field, it's going to experience a force. And that direction of the force is going to be predicted by Fleming's left-hand rule. So you are going to say the force of the force of the electric field is upward, which is usually shown by the thumb. The direction of the current, yeah, is in that direction. So you are going to place your finger like this, so that you cannot, guys, you cannot be able to see from there. You cannot be able to, let me just, yeah. So I'm having my conductor here. I'm trying to see if I can be able to demonstrate so that you can be able to see, guys. Yeah, so this is the conductor. Yeah, trying to show you how we can be able to achieve that. So you can see this is my left hand rule, my left hand. So I'm going to position field. I don't know in which direction will be acting, but the current is going in this direction. Yeah, the direction in which the charged particle is moving is that direction. So I should place my finger, this finger, so that it's in that direction of the current. Yeah, yes. Then the force you see is upward. So the thumb, my thumb is pointing upward, and the field, the current finger is pointing the way the particle is moving. The thumb is pointing upward. So which means that the field will be going into the page, the way this finger is pointing into the page, so that this will be upward, the current finger is in that direction. So I can be able to say the electric force is going to be downwards. Yeah, the electric force will be downward, so the magnetic force will be upward. If the magnetic force is upward, then it will mean that the field must be into the page. The field must be into the page. I'm just using Fleming's left-hand rule, and I believe that one is now okay. You can be able to see clearly. So let's go back to our class. So that's why I'm saying that the electric force is downward, so the magnetic force must be acting upwards, and the magnetic field is into the page, and that we have used Fleming's left-hand rule to display that. Then we are told in the next question that the velocilector is used to produce a beam of oxygen ion traveling in a straight line with speed of 5 times 10 to the power 5. Calculate the magnetic flux density. Remember, in this particular question, we are going to say magnetic field is equal to the electric field. So that is exactly what I've done at this particular point. Magnetic field is equal to the electric field. Then if you make, you can see Q and Q will cancel out, and then we are going to end up remaining with magnetic field is equals to electric field divided by the velocity. If you work it out, you are going to get your answer 0.021 Tesla. After passing through the velocilector, the beam of oxygen ion with the same velocity enters the region of uniform magnetic flux. The different isotope of oxygen can be present in the beam. Explain why the detector will only detect one particular isotope. So we need to remember that isotopes have different masses, and the magnetic force will be the same because the charge is the same. Different mass will lead to a circle with different radius, so only one isotope will be detected. Only one isotope will be detected at that given point. In this question here, we're told that a student investigated electromagnetic braking using the apparatus shown. A vehicle consisting of a glider and aluminum plate was placed on the air track. A powerful magnet was positioned between the two light gates so that the aluminum plate will pass between the poles of the magnet. And that's exactly what's being displayed here. As it's passing here, it will pass at a given velocity. Then once it's going to pass, this aluminum plate is going to cut through the magnetic fields. The vehicle was given a push. The aluminum plates took 0.19 to pass through the gate 1, this gate 1 here. Then you are supposed to show that the momentum of the vehicle was about 0.3 Newton seconds. And then remember, speed is equal to length of the speed is going to be the length of this particular aluminum plate divided by the time it will take to run across there. So this is going to be 0.789 meters per second. But momentum is given by the formula. Momentum is equals to mass times velocity, which will mean that if you do the calculations at that point, you're going to have your value as 0.3156 Newton seconds, which is approximately 0.3 Newton seconds as it was given at that point. Then also we are told that the vehicle is then moved between the poles before passing through the gate 2. The magnet caused the kinetic energy of the vehicle to reduce by 10%. So meaning we can be able to get the kinetic energy when it passes there. But we shall say initial kinetic energy is equals to the new kinetic energy. The final kinetic energy will be equal to the original kinetic energy times 0.9. Why 0.9? Because we are told we reduce by 10%. So the kinetic energy that will be remaining will be 90%. So 90% as a decimal will be 0.9. So that's why you can see my new kinetic energy will be original kinetic energy times this value. But the mass, remember, will be the same for both cases. So mass will cancel out, and if you work out the final speed, is going to be 0.749 meters per second. That's the final velocity it will be passing through the second case. Explain why the current was produced in the aluminum coil. Now this is the concept of electromagnetic induction. When the coil could pass through the poles of the magnet, that is going to cause what we call electromagnetic induction, because the aluminum coil, as the aluminum coil passes through the poles, the aluminum plate is going to cut through the field, and when a conductor cuts through the field, there is a change in magnetic flux within the conductor. As it's cutting, then there will be an induced EMF. So we are going to say, as the aluminum passed through the magnet, there was a change in magnetic flux, which led to induced EMF in the aluminum, which resulted to a flow of current. When there is induced EMF, then it means there's going to be a current flowing. The kinetic energy of the vehicle decreased as the aluminum plate moved between the poles of the magnet. Why? Remember, when the aluminum plate moved between the magnets, what is going to happen is that there will be an induced EMF in the aluminum coil. Yeah, and that induced EMF will be flowing in such a way that it's going to create a magnetic field which is going to oppose the change causing it, according to Lenz's law. So we are going to say aluminum moves the magnetic field. Electrons in the aluminum experience a force which we call Lorentz force, which cause them to move, causing the current within the metal. According to Lenz's law, the direction of these induced eddy currents will be such that they create a magnetic field or electric field that oppose the change that produced it. So in that way, there's going to be an opposing force in the process. If you are asked to show whether quantities are proportional, you need to show that there is a constant. So if I take thickness over the percentage reduction for each of the case, I'm going to get 20, and I'm having a constant for all the values, and that is going to show that this shows that kinetic energy is proportional to thickness. Suggest why the percentage reduction in kinetic energy increases as the thickness of the plate increases. We are going to say from R is equals to resistivity length over the area. Now you can see the current will increase, inducing an EMF, and once there will be an induced EMF there, which will be the same, then the rate of energy transfer to the surrounding in this sheet that is having a greater thickness or a large amount of thickness, there will be a high rate of energy transfer to this surrounding, which means that this is going to lead to a high kinetic energy reduction. This is Faraday's law, which is written as induced EMF is equals to the rate of change of magnetic flux linkage, and then you are supposed to state n phi, and this means flux linkage Weber. The unit is what? Weber turns in that case, Weber turns. So in the event you are given a question like this, we are told that 500 tons of coils, a coil of 500 tons and radius 3 millimeters is placed between two poles of an electromagnet as shown there. Determine the maximum EMF across. Now, to determine the maximum EMF, remember here we are given a magnetic flux density. Then you need to work out the rate of change of magnetic flux. And rate of change of magnetic flux times the cross-section area times the number of turns is going to give us the magnetic flux linkage. So the first thing we're going to understand is that rate of change of magnetic flux linkage can be given by rate of change of magnetic flux times the cross-section area times the number of turns. So from this particular graph, what we only need here is the rate of change of magnetic flux. We multiply it to the area, we multiply it to the number of turns, which is going to be the rate of change of magnetic flux linkage. And the rate of change of magnetic flux linkage means that is the EMF induced. The section you're going to use is the section that is going to give you the maximum, the largest gradient ever. The section that is going to give you, you are going to use to find the gradient, is a section that will provide a largest gradient. And if you can look at this section here, this is where we can get the largest gradient. And that's why I identified that. I did draw my my tangent for that curve. Then I worked out the gradient of this, which I got as what? The gradient of this line, which I got as 100. Once you have that gradient as 100, guys, the next thing you are going to do is now to get the rate of change of magnetic flux linkage, which is going to be the gradient times number of turns times the cross-section area of the coil. And you can see here you were told the radius of the coil is what? 3 millimeters. So you are going to convert this to meters and then use this radius to find the area, which you can see I did it here, pi r squared times 500. Then if you work it out, you are going to get 1.4 volts. Yeah, so basically such kind of questions, find the maximum gradients from this graph and then go ahead to work it out. Then some electric motor designed by electromagnetic induction here. Yeah, that's the motor that we are having, the motor for us. This aluminum disc, a magnet is moved. Once the magnet is moved, remember, there is going to be induced current in this particular disc. In the process, there will be magnetic field created around this disc, which are going to interact with the magnetic fields of the permanent magnet. Then in the process, the magnet is being moved down. This disc will start rotating also down, following the magnet. And the purpose of that is to try to reduce the rate of change of magnetic flux linkage according to Lenz's law. Down, we are told, students suggest that the disc will start to rotate as the magnet is moved, and the disc will rotate in the same direction as the movement of the magnet. Discuss this suggestion. Is this suggestion correct? Was this student making a right observation? Yeah, the student was making a right observation. Yeah, because as the magnet is moved, there is an induced eddy currents in the aluminum disc, and this is going to create magnetic field due to the current in the disc. And the field of the magnet will interact with the field that has been created by the current in the disc. According to Lenz's law, the disc will move to reduce the change that is producing it. So according to Lenz's law, the disc will move to reduce this change. And remember, the change is the cutting of the field within the disc. So according to Lenz's law, this will move to reduce this change. Hence, this disc is going to move in the same direction there. Yeah, so we are having Thomson demonstrated electrons are small negative charged particles, and then we are told that this is the apparatus that was used by Thomson. Yeah, we are supposed to prove this. V is equals to potential difference of a magnetic flux density times the distance of separation of the plates. But what the concept here is, magnetic field is equals to the electric field. Remember, electric field is V over D. Magnetic field is Q charge times electric field. If you substitute, Q will cancel out and the velocity V made subject will be equal to the potential difference over the magnetic flux density, like that. Experiment was carried out using similar apparatus, show that the V value is this. So you are just going to substitute in this formula that we have here. Potential voltage is 331 volts, and then we have magnetic flux density and distance there. Magnetic flux density is here and the distance, but you have to remember that distance has to be in meters, guys. You cannot fail just by forgetting that. It's very basic concepts, like correct units. You don't have to fail physics because of just forgetting just units. Units is not something that will make you to fail. Yeah, you have to be looking keenly. You look at question as if your life depend on it. Remember, you are near 13, so you cannot make such a mistake of units. If you do, guys, that I'll be very much disappointed with you guys. Don't fail because of writing wrong units in physics. Yeah, or not converting units in the correct order or in the correct manner. Yeah. Okay, so I think we now need to move further to the next question. And the next question here, we are told when the electric field between the plate is switched off, electrons move in a circular path. Yeah, they move in a circular path. Remember, when we are talking about the presence of magnetic fields are going to produce a force, and the force of magnetic field to a moving charge is usually perpendicular to the direction of that particular charge that we are talking about. So for that reason, these particles which are within the magnetic field, they are going to experience a force, which is magnetic force. And remember, magnetic force is calculated by the formula magnetic flux density B times the electric charge times the velocity at which it's going to move. So if you are going to substitute that into this formula, you're going to have your mass charge per unit mass to be 1.88 times 10 raised to the power 11, yeah, coulomb per kilogram. So that is exactly what you are supposed to leave. Now there is this kind of interesting concept that was a bit amazing, because initially it was believed that electrons are particles. Electrons are particles. But Thomson tried to do an experiment by passing a stream of electrons through a gap, and he directed them to collide with a crystal. Then he was able to realize that there was a pattern, this beautiful pattern that is created here. Yeah, there is a pattern, diffraction pattern. So from this one, it was concluded that electrons can behave as particles, which is shown on photoelectric effect. Also, electrons can behave as waves, which is the reason as to why we are having diffraction patterns. So a diffraction pattern will only be observed when we are talking of a wave. Interference and reflection will be observed when we are talking about waves. So when an electron displayed this amazing and beautiful pattern, then it indicated that waves can behave as electrons, electrons can behave as waves. At the same time, electrons can behave as particles. Then they concluded and say the duality nature of electrons. Duality nature of electrons means electrons can behave as waves or particles. So the question that we were being asked here, explain how this pattern that was discovered here, how did it change the understanding about the nature of electron? Since the electrons showed diffraction, then they were understood to be acting as waves. And that is exactly what you are supposed to write here and say the diagram shows an interference pattern, diffraction pattern, which can only be observed with waves. So it was concluded that electrons also behave as waves. So the next part that we are having here is a force on a current carrying conductor. This is quite sweet, quite amazing, that if a conductor carrying current is placed within the magnetic field, that's why we are having this magnet here, so that we shall be having a series. We are going to be having a series of magnetic fields here. Yeah, we are going to have magnetic field at that particular point. So meaning this conductor is going to experience a force, and anytime you are calculating a force experienced by the conductor within a magnetic field, guys, remember the only formula you are going to use is force is equals to magnetic flux density times the current, amount of current, times the length of that particular conductor, times sine of theta. And the angle theta is the angle between the current and the field. So fields will be going that direction, currents going this direction. So they are forming which angle? 90 degrees. They are forming 90 degrees there. So this is going to be sine 90. And sine 90 is 1. So if you work it out, you're going to get the amount of force is 0.0636. Sorry, the length of the conductor, because here we were given the force. Yeah, we were given the force, and the force is 2.8 grams. The force will be measured here. Then for you to calculate the force now, you do the weight. You calculate the weight of 2.8. So first you convert this 2.8 into grams, to kilograms, into kilograms. Then apply force. Weight is equals to mass times gravity. So mass in grams is this. So a kilograms is this one, times 9.8. Then we shall say will be equal to BIL sine theta. Then if you substitute everything and work out the value of L, the length will be 0.0636. So we can be able to calculate the amount of force that is acting on a conductor like that. So basically, that's what you are supposed to do. That's what you are expected to do in that particular question. So moving further so that we can be able to see the next question. Here we are given a conductor which is placed within the magnetic field, and then the examiner expected you to state which of the following graph shows the force on the wire carrying current on the wire as theta varies, increases from 0 to 90. So you remember, as the angle increases, the amount of force experience also increases. But the most important thing that you need to remember, guys, is that force is equals to BIL, isn't it? Magnetic flux density times current times the length. All these guys, these values here, they are a constant. The only varying value is the angle. So this is going to be F is proportional to sine theta, and the sine graph is usually like this. So which one is behaving as a sine graph? Is part B. Yeah. So that is going to be current will increase and then it will reach maximum, then it will start going down. Huh? So that's the correct value that you are to leave there. So guys, thank you for watching Proflan YouTube channel. If you would like to proceed and continue working out these questions in this worksheet, consider checking in the description. There is a link that will take you to the Patreon page where you are going to download this PDF so that you can be able to continue learning. I believe you got value from this video. I wish you all the best in your exams. Good luck, and don't forget to share the Proflan YouTube channel to your friends. Don't forget to subscribe. See you in the next tutorial.